So, welcome once again to convex optimization, and in this journey that we are taking together, we are going on the main routes as well as taking little bit of detours, which is fun, I guess, and we will continue doing so. So, today we will talk about saddle point conditions as I had promised in the last class, but also something I will do if I have time by the end of this lecture is to give you a list of functions and their conjugates. You can try to figure out whether what I write down is correct or not, could be your homework. So, here again I am considering this problem, minimize a function f subject to inequality constraints and x being equal to x being an element of x, where capital X is an closed and convex set in Rn. And these are convex functions f and gi's. So, essentially we are talking about a convex programming problem CP. Now, these functions are not assumed to be differentiable. So, they could be just, but they are sub-differentiable, obviously they all have a subgradient at every point, and so this is quite a general form of convex function. Now, what could be x? So, x is, this is called an abstract constraint. This is, this is an inequality constraints given by inequalities, and this is called an abstract. This constraint is called an abstract constraint. This is called an abstract constraint. So, what will be the form of this x? Okay, x could be anything. X could be, for example, Rn plus, that is, it has a non-negativity restriction on the variable, or x could be the Cartesian product of say n intervals in R, or x could even be so you got a many forms of x. So, that is why it is called an abstract constraint. So, all these forms can be written in this thing. There could be additional inequality constraints also, which you just want to hide for some reason. Now, so that is why we do not have any particular structure on x when we discuss this. Now, the question is there a necessary and sufficient optimality condition? Now, you say, okay, what is the problem? Replace gradients with sub differentials and say 0 belonging to something, some sub 0 belonging to del f x naught plus lambda del g x naught and all those things. But the question is that suppose we do not know anything about sub differentiability either. Is there a more fundamental way of looking at it? Just looking at what means point x bar to be a minimum of such a problem, and then try to figure from there if we come to any conditions. Now, let me tell you one thing, that when a theorem gets discovered in mathematics, it is done through a lot of guess and test. Means it is not that somebody comes in the morning, takes a cup of coffee and writes a theorem and gives the proof. No, it is not like that. It is largely done by guess and test, someone trying to play around with something, doing this, doing that, then trying to gradually put some idea in, then later on refined by people, and gradually a refined version comes, and which we read in textbooks, and which gives the impression that somebody had really taken a good cup of coffee in the morning and just came and wrote down the theorem with the proof. Now, suppose I am to look at this problem, and I have been given this problem, I really do not know what to do about it. I have told that let x bar be an optimal solution, or minimizer, whatever, because you are minimizing what condition x bar would satisfy? I only know that they are not differentiable, and I suppose I do not know anything about subdifferentiability. Then is there any way I can start off? If I am to figure such things, then possibly I would think in the following way. Okay, how do I go about it? See, what can I say? What does it means that x bar is a solution? So, I will look at the very fundamental thing. Since I have no weapon in my hand to directly attack it, I look into the very basic thing. It is always good to tickle the basics a while sometimes. So, this means that this system, there would, for every x of this form, this is what is going to happen. So, f of x minus f x bar, if this is strictly less than 0 and you have, that is, you will, for every x satisfying this would happen, but any x which is satisfying this, any x which satisfies this cannot satisfy this, because x bar is a solution of the problem. Because if there is an x which is feasible to this original problem CP and also satisfies this, means which it has a value which is better than x f of x bar. So, then you cannot say that x bar is a minimum, but we have guaranteed that x bar is a minimum. So, x bar minimizes the function. So, over the constraints. So, this system does not have a solution. Now, what is the meaning of writing that? Why I have written it like this? See, a large issue, the central issue in optimization as far as optimality and all these things are concerned revolves around the separation theorems. So, now I want to put everything in a form when separation takes place. What I am going to try to show that optimality means that some intersection of some sets are empty, or intersection of two convex set is an empty set, they do not intersect. So, if optimality is reached, so using x bar I can define certain sets for which their intersection for those two sets would not intersect, and as a result which you can apply a separation theorem. So, instead of going into the details, I want you to figure out, can you express this analytical fact geometrically? It will be a very good exercise to show that this is equivalent to the fact that two convex sets have empty intersection. Means basically you have to find those convex sets. Now, in optimization theory lot of such systems come. Will you keep on applying these systems, right? What I want to look into is further. I want to say that okay, if x bar is a solution, then this system has a solution. So, you see if this system has a solution, then it is obvious that this system has a solution. So, why I have taken off the equality here and made it strictly inequality, because that allows us to apply the separation theorem in much easier form. So, instead of really applying the separation theorem, whatever we need to apply there can be put into the form of a result called the Gordan's theorem of the alternative. The proof of this result is promised for the next class, not now. The fact is that what is the theorem of the alternative? The term alternative means there are at least two things. So, there will be two systems, system 1 of equalities and inequalities. So, what does system 1 say? System 1 says, for example, for the Gordan's case, is that I have m convex functions from R n to R. So, this system means there find an x for which all of these are strictly less than 0, all of these convex functions, and there exists 0 not equal to lambda element of R m plus such that lambda 1 f 1 x plus lambda m. So, this theorem is a consequence of separation principles. So, what does it say? There are two systems, system 1 and system 2. System 1 says that there is a x for which this will have a solution, there would be an x for which all these strict inequalities are valid, and the system 2 says that there exists a non-zero lambda in R m plus, that is all the components has to be greater than or equal to 0 with at least one non-zero, such that this non-negative linear combination of f 1 f 2 f x f m x is greater than equal to 0 for every x that you choose. Now, the result says any one of the above has a solution, but not both. So, once this result is given to you, you say hooray, now I have an immediate approach, I can tackle it. You see these f 1 f 2 f n's, just to keep you posted on this fact that we are always using convex functions. Okay. So, this means any of the system, if this system there is no x for which this is true, then this must be true. So, in our system what we have is f x minus f x bar. F x bar is a fixed quantity, right. This is a convex function and g 1 x slightly. So, if x bar is a solution, this system we know does not have a solution. So, this corresponds to something like system 1 here in the Gordan's theorem of the alternative. So, now which means, so there would exist. So, this if this does not have a solution, then the second must have a solution. Only any one of the above systems, any one of the above has a solution, but not both. The interesting fact is that one of them would have a solution. If this is not having a solution, then this will have. It cannot be that both are not having a solution. If one does not have, the other has. That is the interesting part. That is what it means by the alternative. One of the two always has a solution, but both of them cannot have a solution at the same time. So, now, so again I want to reassert, these two systems both cannot be unsolvable at the same time too. So, if this is unsolvable, then immediately this will have a solution. So, you see here x is the variable, unknown variable, and here lambda is unknown variable. So, you have to be very careful. So, if this does not have a solution, this will immediately have a solution. So, one of them would always have a solution, but not both. Neither both would be unsolvable at the same time. So, there would exist lambda naught, this lambda naught is corresponding to this set greater than equal to 0, lambda 1 greater than equal to 0, dot 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 lambda m greater than equal to 0, such that the vector lambda naught, lambda 1, lambda m, this vector is a non-zero vector, and such that this is non-zero, and lambda naught So, I have applied the Gordan's alternative theorem. So, here we shall apply the Gordan's theorem of alternative. So, we are essentially applying this result always, Gordan's theorem of the alternative. So, once I have this, I do not know, suppose lambda naught could be 0 here at this point, because then of course, f would go out of the description, and that would not be a fair thing to do. So, the interesting part is as follows. Let me do one thing. Now, let us impose a condition, because we say this system does not have a solution, means if there is an x which satisfies all this, then that x cannot satisfy this. It has to be, that would be greater than equal to 0, that inequality. So, essentially some way we are assuming some condition like the Slater condition. So, let us assume the Slater condition or the Slater constraint qualification. Now, once I know this fact, then what happens? That is, there exists an x hat such that g I x hat is strictly less than 0 for all I. Then, if this is the case, if this is the scenario, then what would happen? Let us see. Do we have some additional information? If this happens, if the Slater condition is true, if Slater holds, then lambda naught is not equal to 0. Why? The question is lambda naught is not equal to 0. Now, suppose lambda naught is equal to 0, then this part will vanish. This would imply there exists a x hat element of x. Now, if I take, so this for every x, so for the, in particular for the x hat. So, in particular now you can see what is the game. There will be a contradiction because each of g1x, g2x, gmx hat these are all strictly less than 0, where x hat is element of x, and lambda 1, lambda 1, lambda 2, lambda m all are greater than equal to 0, but since lambda naught is equal to 0 and this vector cannot be equal to 0 completely, one of the lambda 1 or lambda 2 or lambda m must be non-zero. So, which means what we actually have is that we must have lambda 1 g 1 x hat g 1 x hat So, this contradicts this one. So, finally, we have a contradiction. So, lambda naught is not equal to 0. So, what I now do, divide by lambda naught. Lambda naught, this fact, this equation. So, what I get is the following, then because lambda naught now has to be strictly bigger than 0, that is lambda naught is not equal to 0 means lambda naught is strictly bigger than 0. Then what we have now is so, this is what we will have. Now, what I will do is that write lambda I bar is equal to lambda I divided by lambda naught bar, right. I will do this. So, then we have f x minus f x bar plus lambda 1 bar g 1 x plus lambda m bar g m x is greater than or equal to 0 for all x in x. Now, set x equal to x bar. Let us see what happens if I do that, because this is true for every x in x. So, just out of curiosity, just put x equal to x bar, which is quite natural to have such a curiosity. then if that is so, then this part will go. So, I will have lambda 1 bar now, because x bar is a solution, all of these are actually less than equal to 0. Since x bar is a solution, then g 1 x bar less than equal to 0 because it is feasible, g m x bar is less than equal to 0 and x bar is naturally element of x. So, this would imply knowing that these are, so this would also be greater than equal to 0. So, not lambda naught bar, it is lambda naught. So, you divide by lambda naught, which is non-zero, strictly bigger than 0, all these greater than equal to 0 quantities. So, it would imply that lambda 1 bar So, I have these two equations to compare and this would result into the fact that lambda 1 bar g 1 x bar equals to 0. Now, your homework show that this implies so low. I have got the complementary slackness condition which I have already discussed earlier while finding optimality conditions. So, you now think that we are actually on the right track because we have got something which we know and which you know is very fundamental. So, we must be on the right track. So, knowing something, knowing that you are on the right track gives you certain enthusiasm. So, let us go back to the formal equation again. So, what would you have is now f of x plus lambda 1 bar g 1 x lambda m bar g m x is greater than f of x bar. But I can, because this is, I can write this as as f of x bar plus 0. Why do I write this? Because you see this part is 0 and this part is quite similar looking like this part. So, I can write this as so now there is a commonality in the appearance of these two expressions. It says this is bigger than this. Now, this would simply say this can be shorthanded and we can write this as L x lambda bar, where lambda bar is lambda 1 bar, lambda 2 bar, lambda m bar is bigger than lambda L of x bar lambda bar, means we are defining. So, this is called the Lagrangian function, which you also have studied when you have done your basic mathematics at your first year level in calculus, Lagrangian function, but this is extremely fundamental to optimization for our problem CP, the Lagrangian function is, it just takes the non abstract constant, the inequality or equality constants, and adds them to the constraint. That is an attempt to make a constant problem on constant, but here the abstract constant cannot be handled or pulled into the Lagrangian. It can be, but it would involve a bit more technicalities which we need not go, and because without the technicalities we can get what we want. For the Lagrangian function is Lx lambda for any lambda where this is in Rn and this is in Rm plus. So, is defined as f of x So, this now would be defined like this, and this obviously is defined like this. So, this is true for all x in x. So, because I have not chosen that it is only for a x which is feasible. So, this is for any x in x, this is true. So, I have shown the existence of a lambda bar such that this holds. So, this and where this is what is called the Lagrangian function. But also look at this fact. The fact is the following, that let so observe the fact, observe this. Now, take any lambda in Rm plus, lambda, any lambda whatever you want, then lambda 1 g1 x bar lambda m gm x bar is less than 0, naturally, because all of these are lambda 1, lambda 2, lambda m are in Rm plus. So, they are all greater than or equal to 0, and g1 x bar, gm x bar, they are all less than or equal to 0, because x bar is a solution. So, this would imply f of x bar plus lambda 1 g1 x bar. Now, you add f x bar on both sides. Right. Then you can say, okay, how do I make them look alike? So, I can add 0 again and put 0 whatever you know as 0. So, what I have proved here is L of x bar of lambda is less than L of x bar of lambda bar for all lambda in Rm plus. So, what I have shown that if x bar is a solution, then there exists a lambda bar where all the lambda 1 bar, lambda 2 bar, lambda m bar are bigger than or equal to 0, and once I fix the lambda bar, the Lagrangian becomes a function of x, and in that state it minimizes, the Lagrangian function is minimized over the set capital X. So, once I fix up the lambda bar, you see x bar minimizes this function, while if you look at this one, it says that if I fix up the lambda, fix up my x bar and I vary my lambda. So, if x bar is a solution, I can always get a lambda bar such that if I fix up the x bar and vary my lambda, this lambda bar is maximizing L x bar lambda. So, x bar, what lessons learnt is x bar minimizes L lambda bar maximizes So, the all this story that we were telling can now be summarized, that if x bar is a solution to Cp and Slater condition holds, there exists lambda bar in Rm plus such that number 1 L of x bar lambda is less than equal to L of x bar lambda bar is less than equal to L of x lambda bar for all x in X, and lambda is element of Rm plus. And of course, we have to mention the complementary slackness condition. So, together this is called the saddle point condition. So, this is called the saddle point condition, this is the complementary slackness condition. So, this condition 1 is called saddle point condition. This is the most fundamental necessary condition for a convex programming problem. The reverse question has to be asked, that if I have an x bar and a lambda bar for which these two conditions are satisfied, then remember here I have a lambda I bar, this is important, not lambda I. So, if these two conditions are satisfied, I have an x bar in X for which these two condition holds, is x bar a solution to the original problem? That is exactly what we need to prove now. Now, let us go for the converse of what I just said, that okay, if there are points x bar and lambda bar which satisfies this, what would happen? Is x bar a solution of the original problem? Now, x bar here is the element of x, I do not know whether it satisfies g I x bar less than equal to 0 or not. So, suppose x bar is not a feasible element, now this means that if I write down g1 x bar, g2 x bar, gm x bar, there is one of them which is strictly bigger than 0. So, if I am writing this, then one of these quantities is strictly bigger than 0, any one of them. So, that means that this vector cannot belong to the negative of Rm plus, in the sense that all of them are not less than equal to 0, but Rm plus is a closed convex cone and this is the point outside it. So, there exists P element of Rm P not equal to 0 such that, now here we are applying the strict separation theorem. Such that P of g x bar P and alpha, sorry I would write, and alpha element of R, so that P of g x bar is strictly greater than alpha is strictly greater than equal to P of V for all V element of minus Rm plus. We had been using this when we had proved k not equal to k. In the last class, we had also used a similar result. Now, let us see. Here you can put a equality also, does not matter much. So, if this is my strict inequality, so basically P x equal to alpha is the hyperplane which is strictly separating this point g x bar with v. What I claim is that see v put v is equal to 0 because R m plus has 0. This would imply that P of g x bar is strictly bigger than alpha, strictly bigger than 0. So, what you have proved here is P of g x bar is strictly bigger than 0. Now, what I want to prove is that P of v is less than equal to 0 for all v in minus R m plus. Now, this means what? Now, suppose P of v is, so there suppose there exists v tilde such that P of v tilde is strictly bigger than 0. Suppose this is not true, then this implies P of lambda v tilde is strictly bigger than 0 for all lambda is element of R plus, that is lambda for all lambda strictly bigger than 0 or plus plus. As you take any lambda strictly bigger than 0, this will be true of course. Now, lambda of v tilde is also an element of minus R m plus, which is quite natural. All the vectors would remain, all the components would remain negative. So, I can make the lambda bigger and bigger and bigger. So, remember yesterday's arguments. So, it will be bigger and bigger and bigger, and so if this becomes bigger and bigger and bigger. So, this value can then for certain threshold value of lambda would cross the value of alpha, would become strictly bigger than alpha. So, as lambda tends to plus infinity, there exists lambda naught such that for all lambda bigger than lambda naught, P of lambda v tilde is strictly bigger than alpha, which is a contradiction because it breaks this fact. Now, once I have broken that, we have a contradiction. So, we have that now that P of v is less than equal to 0 for all v element of minus R m plus. So, for every negative number, this P of v has to be less than equal to 0. Basically, find all the vectors P. This is your R 2 minus R 2 plus. So, find all the vectors P which form an obtuse angle with elements here, which means all the vectors here. Basically, so this implies P is element of R m plus. Now, what do I have? So, that now shows that P is element of R m plus and P of g x bar is strictly bigger than 0. But I have that L of x bar of lambda is less than equal to L of x bar of lambda bar. Now, so this is true for all lambda. So, L of x bar of P, because P is also for all lambda in R m plus, this is true. So, since P is in R m plus, so putting lambda equal to P, it implies that this is less than L x bar lambda bar. So, this would imply f of x bar plus P1 G1 x bar P2 sorry PM GM x bar less than equal to f of x bar, but lambda 1 bar plus lambda 2 bar plus lambda 3 bar lambda m bar this lambda 1 bar G1 x bar lambda 2 bar G2 x bar lambda m bar G x bar, that is equal to 0. So, that part I am not writing. So, this would imply this cancels from both sides. So, this would be less than or equal to 0, which shows that P of G x, this can be put into this form naturally, P of G x bar is less than equal to 0. So, this is a contradiction. So, we come to a contradiction. So, proofs by contradiction are sometimes fun, it gives you the answers immediately. So, which implies that what we have assumed is not correct. So, G of x bar is an element of minus R m plus, which implies that x bar is feasible. Once you know that x bar is feasible, then immediately you also know this equation L of x bar lambda bar is less than equal to L of x lambda, sorry L of x lambda bar. So, finally, you will have f of x bar less than equal to f of x plus lambda 1 bar G 1 x but you see, if I take x to be feasible, then all of this x. So, this is true for all x in x. So, if x is feasible, then apart from being x in x, they should also be satisfying G 1 x less than equal to 0, G 2 x less than equal to 0, G m x less than equal to 0. So, this whole part becomes negative, because lambda 1 bar, lambda 2 bar, lambda m bar is non-negative, they are greater than equal to 0. So, this part is, this is true if x is feasible, and that gives you the answer. So, f x bar is less than f x for all feasible x. So, that is what we have proved. Now, there are a lot of things that come out of this, but we will not do this thing. Now, as I promised, I will give you a table. We had spoken about f star of a function, the conjugate of a function, but we have given some little examples. We will give some more examples today, which so that you can figure it out nicely. So, I will have f, I will write down dome of f, I will write down the f star, and I will write down the f star x star, basically f star x and dome of f star. So, I will write down few functions and just so that you can have a listing. So, 0, the dome of f is r, it is 0 function. This is also 0 function, but the dome is other than 0, it is plus infinity. You figure out, this would be your homework to figure out what I am writing is true or not. So, the dome f is r plus. So, these are, we are only talking about proper convex functions. So, if it is r plus, means anything else other than r plus, the value of the function is 0, the value of the function is plus infinity. So, x is in R, our x is in R. The domain is R. The domain is R plus plus, obviously, otherwise you cannot define log x. The domain is naturally minus R plus plus. So, these what I am giving you is a collection, these results are from, I will just write down the name of the book, which will be very important for your studies, those who want to really get involved into convex analysis and optimization, this is the book we should really start with at this moment. This is a very modern, very well written, a fascinating book. I will just, and I am actually listing them from this book, and of course, this is one of my own favorites. So, these are some examples. So, what are this listing is given from the book Convex Analysis. Borwin and Lewis, James Borwin and Adrian Lewis, they are very famous optimization theorists, and Borwin basically is a polymath, and this is published by Springer, the first edition in 2000, and now you have a second edition. So, I can just even show you this book if you really want to look into the title. Once again, this book should be the starter for anyone who wants to graduate in this area of convex analysis and optimization. So, this should be the starter book, and this is also one of my very personal favorites. Trying the problems of this book is by itself getting into research, really doing research. Some problems in this book can actually lead to some research. So, with this I end up my talk today. Thank you very much, and tomorrow we will see the consequences of the saddle point theorem.